This is part one of Chem Inquiry 3. In this part of the experiment, we're going to try and separate the C60 and C70 buckyball mixture that we formerly extracted from the soot during the lecture. So let's take a look at some of the things that we did. In the first vial over here on the right, we've got that powdered soot that has C60 and C70 in it. Just looked like regular soot. And you saw that in class we mixed it with toluene, which is this colorless organic solvent. And when we did that, we ended up with what was in this third bottle over here, which is that mixture. And right now, it looks kind of like a wine-colored solution on top, but if we shake it a little bit, it gets all sort of dirty. And that's because there was some leftover soot that didn't contain any of the C60 and C70 in it. And so what we would have to do is to get a pure solution of the toluene with just C60 and C70, we had to filter out that leftover soot. And that's what we obtained, this big old jug of it here. You can see this nice wine colored, it's nice and clear, there isn't any solid left in there. So now we're going to think about what that is. So the reason it turned sort of that color in the first place is because C60 and C70 each interact with light a different way. They absorb some of the visible light, and what's left is you see it as this color. Now we're going to use a technique called chromatography, kind of like a fancy filtering technique, which is going to separate the C60 and the C70. So let's take a look at that apparatus. And so all that really is a thing called a column. This is a very, very simple chromatography column. We're just using a glass tube. This is actually a burette. We don't have to use a burette, but it's very convenient. The main part of all the action happens down here at the bottom. And so you can see that that little orange handle, that's a valve called a stopcock, and it's in its open position right now, and that would let liquid flow through. But the most important thing is that black little powdery column. That's actually a mixture of activated charcoal and high purity silica sand. So we're just taking sand and charcoal, and what we'll do is in a minute here we'll pour the mixture of C60 and C70 into the tube, and it will kind of trickle through that black column, and it's going to drain into these little vials down here. And the key thing to think about is that C60 and C70, as they're being washed through that column, have different degrees of stickiness for the material in the column. So the C60 tends to not want to stick to the column very much, and so it gets washed through really fairly quickly. But the C70, because of that slight difference in its shape, just an extra 10 carbon atoms around the circumference, around the diameter of that buckyball, causes it to have sort of a different interaction with the column, and so that gets stuck a little bit more, and as it's washed through, it's sort of dragging its feet, and it's going to come out of the column much later. So the column, when it works, it's going to continue to flush through. We should start to see some C60 come out first, and then later we'll see C70. So now we're going to load that column, it's called. I'm going to take that mixture, that is those two things. So you have to kind of appreciate that this column can separate things at the molecular level. This would not work with a coffee filter. Coffee filter is good for mixing out or separating out a variety of chunky things, things that are large and particulate. But how do you separate things at the molecular level? You use a chromatography column. And the idea, the trick in doing chromatography, it's a really, really popular technique in chemistry, is to choose a column that has the right kind of stickiness for the different molecules you're trying to separate. So instead of mechanically filtering out, this is not like mechanically filtering out like your coffee filter. It's not just sort of getting caught up in the fibers mechanically like you would with a sieve in your kitchen when you're straining spaghetti. It's actually through molecular interactions. We'll talk more about that in Chem 222. Well, anyway, so we can start to see right now as some of the first liquid comes filtering through. This is toluene solvent, mostly by itself. So far, toluene has the least attraction for the column. And it already has got a slight pink color, and so it's already starting to wash out some of the C60, which has that sort of lavender pinkish color. But we don't see, it certainly is going to look different than the original mixture that we had, which kind of looked like red wine or kind of a brownish wine color. So right now, because C60 is not interested or attracted to that column very much, it's just being flushed out along with that toluene. But the C70 is staying behind. It's moving much more slowly through the column. So what's going to happen here is we're going to let this video run, and every so often we're going to swap out these vials of fractions, they're called, the things that are collected. It's a fraction of the total amount of the column that we started with. And so what you'll want to look for as you kind of watch through this, or you can advance forward through it in your video, is to see if the color changes. And then once we get done with that, we're going to save these and use them in a later lab, and we would analyze that if we do that part of the experiment. Alright, so we're going to collect this as our final fraction. Just putting a collection vial under there to collect any of the remainder. Let's zoom in and take a look at what we see here. So as we go from the right side to the left side, we can see that there first starts out just the colorless solvent, toluene, that came through very rapidly. And then we see in the first vial on the right that that's a nice sort of a purpley color. That's the color of C60. And so a large portion of the C60 made it through very early. As we move to the third one from the right, we start to see a little bit of a more red color come in. And so now the tail end of the C60 is finally just sort of finishing coming out of the column. Sort of like a crowd of people, they don't all pass a point at the same time. There's some leaders, and then these are the tails, so to speak, of the C60, and they're kind of crossed over with the leaders of the C70. So in between, in the third, fourth, and fifth vial from the right, these are actually mixtures of C60 and C70 that are slowly enriching in C70. And then the last vial here on the left should be the one that is almost all C70. There's still probably some C60 in here. I should just make a note that this is not a perfect separation. We could tweak it a lot more and play with the size of the column and maybe the solvent or the composition of the column, so that the C60 group and the C70 group are really, really separated, where you might see in between those two there might just be some solvent, toluene, coming out before the C70. But this was just sort of a quick demonstration to show you that by chemical means we can have a separation of things at the molecular level. This is not really a sieve in the same way you would have in your kitchen. This is something that is caused by the molecular interactions of the molecules themselves with the column. So that is a separation of molecules of C60 and C70, and the other point of that was just to show you that how tiny changes in composition and structure can actually have dramatic differences in their properties. And I want you to think about the differences that we saw. One difference was how attracted it was to this column of sand and activated charcoal. And another obvious difference right here is the color, the way that they interact with light. So an extra 10 atoms around the middle changes dramatically how you interact with the outside world. And so in chemistry, one of the big lessons is that structure determines function. And we can see that really clearly here. That's interaction with the outside world, which is what chemists are concerned about, is very, very connected to the structure. This is part 2 of Chem Inquiry 3, the synthesis of 20 nanometer diameter gold nanoparticles. So we've got the experimental setup and the 2 ingredients or reagents that we're going to use to make the gold nanoparticles. So the source of gold is this material here on the left, and we've got the name and the formula up here on top. It's HAUCl4. That is a salt. It's an ionic compound, and the name, one of the common names, is tetrachloroauric 3 acid, and the tetrachloro means 4 chloride ions, and the auric 3 is a way to represent gold. Its Greek name is aurum, so auric is a common name for gold, and the 3 in Roman numerals mean that it's gold in the +3 state. And we need one more positive charge to balance out the 4 negatives, and that's in this particular compound given by H+, and very often that a compound with H+ in it will be an acid, and so that's where it gets its name from. So this is the solution right here. You can see a little bit that it's just slightly yellow, like we would expect from gold. You can just barely see very small yellow tint. So we're going to take that now and add it to the beaker. Got 20.0 milliliters. And then we're going to heat that to boiling, so we'll turn on the hot plate. We're also going to add a magnetic stir bar. So that's waiting to come to a boil. The other ingredient that we're going to add is the sodium citrate, which is over here. 2 milliliters of it I've got on the right-hand side. So while we're waiting for that gold to boil, I've got the heat turned on here. We can talk about what's going to happen. So as you'll see in the next video with silver, the contrast here is that we're going to allow the gold to kind of do unrestricted growth. We're not really going to control the size. But to make nanoparticles, what we need to do is take the gold ions that are in that yellowish solution and carry out a process called reduction. We need to add electrons to them. And if we add electrons to a gold +3, we're going to make gold metal, gold 0. And so gold in that state is not ionic, and the gold atoms themselves would start to stick together. The neutral gold atoms stick together in little clumps. Eventually they just continue to grow in size, and then eventually they get large enough where they would fall out of solution and end up at the bottom. But what we want to do is enable them to stay suspended in the solution. So it's actually, we're going to change our terminology. It's not really a solution anymore, because the particles are going to get so large that they would not normally stay in solution by themselves. They would not stay suspended in the water. So the sodium citrate then, its purpose is to, one, it provides the electrons to the gold 3 plus ions to reduce them down to gold 0. The citrate itself then also gets changed into other things, but we don't really care about that. It's not important for the nanoparticles. But we've added enough citrate so that the citrate also has a second function. That second function is to sort of latch on to the gold metal as it's growing and sort of act as an intermediate between the gold metal and the water. And in a way, kind of like a suspender would hold up a pair of pants. The citrate molecules kind of like sticking like hairs out of the head of a gold molecule or a gold nanoparticle will actually help suspend the nanoparticles in the water. And so we get, it's not a solution because it's not even everywhere. It's not an equal dispersal like you would get with just ions, but you get what's called a suspension. Another name for that is colloid. And at the end of this, we're going to talk about how we can tell the difference by using light. So the citrate in this particular case acts as both a source of electrons, a reducing agent, and also what's called a surfactant, something that is allowing large particles that would normally sink out because they're so large to be able to be suspended in water and make a colloid. So we're going to just kind of wait here until this comes to a boil, and we'll add the sodium citrate, and then we'll watch and see what happens. The key is to kind of watch the color and see what that turns into, and then compare it to how you normally think of gold. So our solution is just starting to boil. So now we're going to add the sodium citrate, and we just want to watch what happens over the course of time. So this takes a little bit of time to develop. You can just advance the video slowly if you want. I don't know if you could see that on the film, but the yellow color almost immediately disappeared. So we're going to watch what happens as we start to get gold nanoparticle growth over the course of time. In the meantime, you should be answering questions on the report sheet, asking for observations as you see this. So there we have it. This is the end of the reaction. It's not going to change color anymore. So the gold particles, I hope you noticed, have gone from being colorless, which means that we didn't have any nanoparticles, and as they grew in size, the way they interact with light changed. And you saw that the result was we went from colorless to kind of a gray to a blue, and then eventually it turned into this sort of a ruby red color, which is characteristic of a wide, diverse population of sizes of gold particles. So that's all we're going to do for the growth of the gold right now. Just back out. So there we've got gold nanoparticles. Later in the lab, a video is going to show us that even though this looks like a solution, but we're going to show you how we can tell that there are actual larger size particles, nanoparticles, and there are things that are larger than individual ions because they're going to be able to scatter light even though it looks kind of transparent. We'll come back to that in a later video for this lab. So this is part 3 of Chem Inquiry 3, the synthesis of the silver nanoprisms. So what we've got here are the reagents and equipment to do this experiment. We're going to do it for you. You'll be able to watch the nanoprisms grow as described in the lab. So let's just run down what the various ingredients are. So on the far left is sodium citrate. That's in the bottle on the far left. Then right next to it in the brown bottle is silver nitrate. Then we've got hydrogen peroxide, followed by potassium bromide, and then this high purity nanopure water. And then finally the last ingredient is sodium borohydride. And underneath each one of those is a small micropipette. And as you can see, it only contains fractions of a milliliter on there. And so that whole entire pipette only holds 1 milliliter. So we're going to be dealing with just a milliliter or two at a time. So each one of those has its own micropipette so that they can't be cross-contaminated. That's very, very important to make this work. And then at the bottom we have our 3 vials. Each one's going to contain a different sample with a different amount of potassium bromide in it, which is going to alter the size of the nanoparticles. And so as you can see left to right, we've got them labeled as instructed in the lab on page 13 of that lab. There's 0.0 milliliters of KBr, and the middle one is 1.0 mils of KBr, and the other one is 3.0 mils of KBr. The reagents for all of the vials are the same except for the amount of KBr. That's the only thing that's different, and that's what's going to change the size of the nanoparticles. So we're going to go and get started now. So we're going to just walk you through in pretty much detail. The first thing we're going to add is 3.0 milliliters of the sodium citrate. That's step number 1, and that amount is going to go into each of the 3 vials. So I'm going to show you real quick here how to use that micro syringe, and we have, since it only contains 1 milliliter, we have to withdraw 3 portions of that. And by the way, when we do this lab, it's the success and the different colors that you're going to get at the end and the sizes are all based on how precise you are in making these measurements. So we're dealing with things that are very low concentration, these solutions, and the particles are very small. So even the change of a half of a milliliter or a tenth of a milliliter error in measuring out the sample size can actually make a difference in the final product that we're about to get. So just to kind of help you remember what each one of these ingredients is going to do in the formation of the nanoparticles. So the main thing that is going to grow the nanoparticles are the silver ions, and that is the next ingredient that we're going to add, and that is silver +1. And you might remember from the introduction that when we're going to grow a silver particle, it actually has to be in the form of metallic silver, which is silver +1, you have to add an electron. And the very last ingredient that we're going to add is something that is going to give electrons to each one of the silver ions and cause them to become silver particles. So as we add these first ingredients, nothing is really going to happen until we add that very last ingredient in steps 8, 9, and 10, which is the sodium borohydride. It's called a reducing agent. And right now, we're going to add 5 milliliters of silver nitrate to each one of these vials. And so, as you can imagine, that's 5 samples for each. This will take a minute. I'll continue to talk about how this growth works. And so, once we get all the other ingredients together, at the very end, we're going to add that reducing agent. Reducing means a reducing agent is something that will very freely give electrons to something else. And so we're going to reduce that silver +1 down to silver 0 or metallic silver. And so when all of those ingredients are together, then all of the different reactions can happen and the nanoparticles can grow. So right now, we've got a mixture of silver ions and we have the sodium citrate. So let's talk about what that sodium citrate is used for. Sometimes the sodium citrate can also act as a reducing agent, a source of electrons for the silver, but its main purpose in this lab is actually to form what you might think of as what we would call a surfactant. In other words, one end of the citrate molecule bonds onto the silver surface, and the other part is very readily dissolved in water. So as you know, silver metal does not dissolve in water. And if we mix this together without any citrate, all our little silver metal particles that are forming would simply just sink to the bottom and it wouldn't be very interesting. So the citrate is kind of the thing that keeps the silver ion or the silver nanoparticles aloft or floating in the water itself. And so it's a very important ingredient. So we're still working away at the silver here. It takes a while to get all these in. And then the next ingredient after the silver will be the hydrogen peroxide. And oddly enough, the hydrogen peroxide is kind of like an oxidizing agent, the opposite of a reducing agent. But its purpose here is to act as what's called an etchant. It's going to etch the metallic silver particles as they grow. So as each silver plus 1 ion is reduced down to silver 0, metallic silver, by the sodium borohydride, particles are going to start to clump together. And they're just going to grow into irregular shapes. But our goal was to create not just irregular shapes, but actually prism-shaped nanoprisms. And in order to do that, you might be thinking, how do we go down there and shave off all the edges of that so it ends up forming a perfect sort of triangular prism? Well, the hydrogen peroxide is the ingredient that's going to work on that. And the hydrogen peroxide will actually react with the silver metal and take electrons away from the silver and make silver plus 1 again. But it only does that along very specific directions in that little crystal of silver, and there's a picture of that in the lab manual. And it turns out that the directions that are preferentially etched away by peroxide are along the edges of a sort of an equilateral triangle. So it's really kind of neat. The hydrogen peroxide won't etch away along surfaces in other directions, but only in those 3. So as this little particle grows, it gets bigger and bigger, but the hydrogen peroxide actually works to keep it in the shape of a triangular prism, of a triangle. So that's kind of a neat ingredient. So we just about finished adding 5 milliliters of hydrogen peroxide to each one of these vials. Again, we're just adding the raw ingredients. Nothing can happen until the starting reagent, the sodium borohydride, is added at the very end. So step 4 is now to get these things to mix really well. So we're going to put the cap on each one, and we're going to shake to mix them. So you can see the reagents still look colorless and clear. So nothing's happening. No nanoparticles are growing. The silver ions are happy to exist in solution with those other ingredients. It's not until we add the final ingredient. So now here's the next thing that we're going to add is the potassium bromide, KBr. And so this is the one that's different for the 3 different vials. On the very left-hand vial, we're not going to add any amount of KBr. But in the center vial then, we're going to add that 1 milliliter, and on the right-hand vial, we'll add 3 milliliters. So what the KBr does is it restricts the size to which these particles can grow in a certain amount of time. And the way it does that is that KBr, potassium bromide, when dissolved in water, breaks apart into separate ions, potassium ions and bromide ions. And the potassium ions are of no significance to us. We don't care about that. Just to cut in here, the next thing we're going to add is the nanopure water. If you look in step number 6 on the lab manual, you can see we're adding different amounts. But if you'll notice, the total volume in steps 5 and 6 totals up to 3 milliliters for each. In that way, at the end of the day, each vial will have exactly the same amount of total liquid in them. So because we didn't add any potassium bromide solution, we have to make up for that volume with water. So remember, when we add these potassium bromide and silver nitrate, those are not bottles just of the pure material, they're just ions dissolved in water. So we want to keep the volume the same, which keeps the overall concentration the same. All right, so now we've got done with step 6, we've got the nano pure water in. I'll just finish off with the potassium bromide here before we do the last step. We're going to mix these up. So nothing's happening yet, but the potassium bromide has the bromide ions, and bromide reacts very strongly with silver ions. And so potassium ions and silver ions from the solution will actually react together to form a salt called silver bromide, which will form on the surface of the nanoparticle, and that will prevent it from growing. It sort of puts a cap on the outside layer, kind of like a shell. And so the more bromide there is in the solution, the more readily that layer or cap on the nanoparticle forms. And the faster that forms and gets completed, the sooner we're going to think about that the growth would stop and the particle would be smaller. So we are going to expect that in the vial with 0 potassium bromide, that's kind of a free-for-all. There's no growth restriction. On the other hand, in the vial with 3 milliliters of potassium bromide, that's going to be the most restricted in growth. We would expect the smallest size nanoparticles of all. All right, so now we're in the next step. We're going to get ready. We're going to add the sodium borohydride, and then we will let the reaction begin, and you'll be able to watch the color change occur. So here we're going to do step 8, 9, and 10. One by one, we're going to add sodium borohydride. That's the reducing agent. That's going to start the reaction. We've zoomed in a little bit on the vials so you can watch the color change. Once these get going, the color change is going to take a few minutes, but you can see this one already. When added in, you can see something happen. It turned yellow, which is definitely not the color of silver metal. So we're already getting some growth of the silver nanoprisms growing. And remember, these are unrestricted, and so they can grow to any size they want. So that looks kind of yellow. We give it a little bit of a mix. And so you can just keep your eye on that as we do the rest of them. So as you watch this, watch the color change over time. That means the size of the nanoparticles is changing. You can see this one's actually changed quite a bit. It's getting quite a bit yellower, turning into an orange. Oh, look at that. So now this is vial number 2. That's a little bit restricted in its size. It's got a little bit of the KBr. And so you can already see how different the one with the 0 KBr has grown to be from the one where this one, when it started, when it was yellow. But this one's changing color as well. They're both continuing to change. Just keep an eye on them. They're not going to stay orange or red necessarily. So already you can see a difference. So I'll zoom in on the first one. So we can see that this is sort of a yellowish brown. That'll continue to develop for a while. You can see the second one has turned blue. And the third one is staying at a yellow color. So we'll see what happens to that over the course of time. So I'm going to let this run for a minute or two, and we'll see if the colors change over that course of time. You can watch this on the video. I don't have much more to say for the moment. As we let this run, you can advance it forward, and we'll see if any more changes occur. Okay, I don't think there's much more change going to happen. I'll show you with some other light on these vials in just a second. So we're going to show you just a few nice looking shots of these three solutions. So you can see that the very leftmost one is sort of the unrestricted growth, kind of a pinkish brown color, I guess. In the middle is the nice blue, and at the very end is the yellow. That's the one that had 3 milliliters of KBr. And so there's some small changes going on, but for the most part these are situated at the colors that they are going to be. This particle size has pretty much settled into its maximum size, and that's what's affecting the color of the solution as discussed in the lab. So here are just a couple other views of these solutions with some bottom lighting. This is the 0. That's 1 milliliter of KBr. And that's 3 milliliters of KBr. So here's another one that we mixed together that had 0 milliliters of KBr. So we'll see if the color is going to develop any differently. So remember, I'll put the other one that we did right next to it. There we go. Do you see the rapid increase in bubbles? So the reaction's really taking off. So in theory, these two were supposed to be the same sample. And it just goes to show you, when you're working with very small quantities, very small concentrations, that even slight differences in your measurements can have a dramatic effect. And so now we see the one that was 0 looks kind of bluish, sort of like the one that we did previously that had 1 milliliter of KBr added. And so this is, you can think about this is one of the reasons why we're so concerned in science with the precision, significant figures, and when we record and take measurements, to be very, very precise and not be sloppy. It's a great example just to see a very small change. When we filmed this, we don't know for sure what the difference was, but there must be some difference in one of the solutions in their volume that gave us a different particle size. Here we're showing all 3 samples from left to right will be 0 milliliters of KBr. The middle is 1 milliliter of KBr, and on the right is 3 milliliters of KBr. We're just going to quickly introduce the sodium borohydride into each and watch and see what the differences are. So these were also produced with 1-day-old reagents. So a little bit different results from when they were fresh. This is 3 different samples. On the left is 1 milliliter of KBr. The middle is 2.5 milliliters of KBr, and on the right is 3 milliliters of KBr. Now we're just going to add the sodium borohydride and watch what happens. pause for a second and do a couple of the other investigations with this. So now we're going to do part 4, which is to see if we actually got nanoparticles in the solutions that we grew. So this is going to start out with a demonstration where we're going to look at the difference of how light interacts with true solutions, where I mentioned in a previous video that these are uniform and homogeneous mixtures of particles that are very, very small, that we can't see with the naked eye, and you can't find different regions or phases of all one type, so they're very evenly mixed. The other thing about it is when we shine light through it, the particles that make up the water and the solution, like right now we're shining some green laser light through a saturated sodium chloride. If you want to shine that laser down at the bottom of the beaker, you can see there's a bunch of solids sitting in there, kind of cool looking. So this is saturated, no more can dissolve. It's holding as much sodium chloride. And so we see that the light beam, we couldn't see the light beam, which meant that the particles are smaller than the wavelength of the light. So that's an indication. It's just kind of a rough test for checking if something is a true solution. And then in the second bottle, we've got some iron nitrate, FeNO33, and we're shining the laser through there. You can't see the light. Now you can see that the laser's on, but you don't see the laser beam scattering off any particles. The ions of iron 3+ and nitrate are still too small. They're smaller than the wavelength of that green light, and it doesn't get scattered. It just passes right through and you can't see it. But on the very right, we've got what's called a colloid. And that laser beam now is being scattered because these particles of iron oxide, which are actually just rust particles, are so large that they are larger than the wavelength of light by a few factors of 10, and they're able to scatter the light. So when we put the light beam through there, what we can see here, if I zoom in on it a little bit, so what's actually happening is that the light is being scattered off of the particles. They're too small to be seen with your naked eye, but when the light scatters off to the side, it gets picked up by our eye. And if we go back to the middle one, just as comparison, you see you really can't see anything. There's a little bit of scattering because these solutions are kind of old and they are not quite as pure as they should be anymore. But for the most part, in a solution, you cannot see the light beam scattering. So that's the test. So now we want to test our nanoparticle solution. So we're going to put them on this little stage here. We're going to add a white light so you can see the color of the solution. And then one by one, we're going to put them on top. So this first one was the solution or the mixture that had 0 kBr, and that was kind of a brownish whatever color. And you can see if you looked at that we could see the light beam. So we must have particles, even though it looked sort of like a solution. We wouldn't call it a solution. This is the second one with 1 milliliter of KBr. We can definitely see the scattering, so we know that we've got particles. We can call this a colloid. And this last mixture was the one at 3 milliliters of KBr, and we can see the scattering as well. So we know we've got larger sized particles. This isn't just a mixture of ions, of silver ions. Something changed and they grew into large particles. This last one is the gold that we made. You can see the bright red color. Maybe we can move that middle one so we can see the middle jar so we can see the red color. There we go. And we're going to use a red laser because it shows up better, but you can definitely see the scattering. So our conclusion here then is, that's for you to answer in the workbook. Do we have nanoparticles, or are these just solutions of ions?